Hi, this is Dr. Pratima back with you. Let us solve some problems from Module 2 of your subject Waves and Optics. Till my last video lecture, we have completed all the concepts of Module 2 and even Module 1 also. If you want to go back and watch those lectures, it will be good for you, especially the Module 2, so that you can learn all the concepts, understand the formulae, and apply all those in the numericals which we are going to solve today. So before going to solve the numericals, let's see the formulae and recall so that it will be easier for you to follow in the coming slides. So first formula goes for the intrinsic carrier concentration, which is given in terms of the Boltzmann constant Kb, and the effective mass, if it might be given in terms of the electron or holes, or because it is the intrinsic concentration, it may be because of both the electrons and holes. So it may be consisting of both the mass of the electrons and holes even. It also consists of the Planck's constant and the temperature in terms of even the energy gap. That's all. Okay. So if all these are given, and if some one of these are not given and asked, then you will have to solve this. Then comes the formula for the Fermi level. So if the Fermi level is asked for you, giving the energy gap, then the energy gap is anyhow, it's equal to EC plus EV by 2. So you can substitute in that. And if there is a shift in the energy gap, you have to consider that shift in terms of the Fermi level shift with respect to the upper level of the valence band, which you commonly take it as EV. If you recollect back in the diagram where we have taken the diagram for the calculation of the concentration of the electrons and the holes. So here again you are able to see the Boltzmann constant, temperature, and MP and Me are the effective masses of the holes and the electrons respectively. And coming to the Hall effect, we have ended up in deriving an expression for the Hall voltage in terms of the Hall coefficient RH, current I, applied magnetic field intensity B, and the thickness of the slab, that is a rectangular slab, T. So even if in your problem you are given the other dimensions like width or anything, you need not take those into consideration, but just take the thickness into consideration, substitute in this formula, and if you are given or if you are asked the number of the or the density of the charge carriers, which are the electrons or the holes, then you can use this formula, which is RH is equal to 1 by Ne. What is RH? It is nothing but the Hall coefficient. So apart of this, you also have from the applications of the Hall effect, where we are able to find the mobility, conductivity, resistivity. Hope you can recollect all of those, right? We know that sigma, the conductivity, is equal to Ne mu, where mu is the mobility. So in terms of the intrinsic carriers, if you have to calculate the conductivity, it is given by this formula, where mu E and mu P are the mobilities of the electrons and the holes respectively. And Ni is the intrinsic charge carrier concentration, and E is the charge of value of the charge of the carriers. And the mobility can be written as, we know that sigma is equal to Ne mu. So if sigma is equal to Ne mu, then mu is equal to sigma by Ne, where RH is equal to 1 by Ne. So it can be written as sigma by RH, but sigma, the conductivity, is inversely proportional to the resistivity. So this can be written as this formula, RH by rho n. And the same, you can also write it in terms of the conductivity as sigma by Ne. You can use this formula and let us solve the problems. Hope you have followed all the formulae and recall even the concepts where and how you have to apply. Coming to the first problem, find the carrier concentration of an intrinsic semiconductor of band gap 0.7 electron volt at 300 Kelvin. You are given that the effective mass of the electron and the effective mass of the hole are equal, that is equal to the mass of the electron. So what is given, what you should find out? First, you have to know, let me What is given? Eg is given, right? Eg is given as 0.7 electron volt and the temperature is given as 300 Kelvin. So what you should find out? Carrier concentration. Okay, so what can you do here? So Ni, you know this formula. So just substitute here. Ni is equal to 2 into 22 by 7 is 3.14 into m star. M star is what? You know m star as 9.1 into 10 to the power of minus 31 into kBt. So kB is what? 1.38 into 10 to the power of minus 23 joule Kelvin into T is what? 300 Kelvin by h square. H square is what? H square is 6.626 into 10 to the power of minus 34 joule second. That's all. Into e to the power of minus Eg is 0.7 electron volt. Here you have joules and here if you have electron volts, it can't be possible. So now let's convert this 0.7 electron volt is equal to how many joules if this is the standard unit formula. So it will be equal to what? 0.7 into 1.6 into 10 to the power of minus 19 joules. Just substitute that here as 0.7 into 1.6 into 10 to the power of minus 19 by 2 into kB is 1.38 into 10 to the power of minus 23 into 300. Okay, so this is a substitution. Just take your calculator, solve it out. So here you will get around minus 54 and you have minus 34. This will go up. Okay, and here also you will have to go for these powers and then you will end up in the answer as 33.49 into 10 to the power of 18 per meter cube. Okay, you can even comment in the comment section with all the calculations if you are interested. So moving on ahead to the second problem, what temperature would the EF is shifted by 15% from middle of forbidden gap Eg? Given Eg is equal to 1.2 electron volt and the effective mass of the holes is 5 times that of the electrons. So what is given first? What is given? Eg is given here. Eg is equal to 1.2 electron volts and effective mass of the holes, effective mass is equal to 5 times the effective mass of the electrons, right? Effective mass of the electrons. So, and there is a shift of the Fermi level. I'll come to it later. So, as of now, let us try to understand this in terms of the diagram. Okay. So, there is a valence band and here is the conduction band which is separated by an energy gap, and this energy gap is given as 1.2 electron volt and this is EV. Let us write this as EC. So EF, which is in the center, can be written as EC plus EV by 2 at 0 Kelvin. How can you say that? Through this formula. At T is equal to 0 Kelvin, EF is equal to EC plus EV by 2, right? So if that's the case, you can also write this EF as EV plus, yes. So this is if this is 1.2 electron volt, then what is this? Half of it. Half of it means 0.6 electron volt. So EF, I can write EF can be written in terms of EV as EV plus 0.6 electron volt at 0 Kelvin. So now you have EF, which is equal to EC plus EV by 2 is equal to EV plus 0.6 electron volt. It's very easy. Now there is a shift. There is a shift of the Fermi level. To how much percent? 15% of shift. So if you consider 15% of shift of the Fermi level, you will get 0.18. For 100, if it is 15, then for 1.2, how much? You'll get 0.18. 0.18 shift of what? So now if I draw for you again, if this is valence band and if this is the conduction band, so this is at 0.6 because this is at 1.2. And now there is a shift of the level. So this EF has shifted to somewhere here. So this shift will be what now? 0.6 plus the shift which you have calculated for 15%. That is 0.18. Okay. So now 0.6 plus 0.18 will give you 0.78. This 0.78 is what? This 0.78 is the shift from EV to 0.78 electron volt, right? From here to here now, the new shift. Okay, so the new shift, if you write it in terms of this, you get EV plus 0.78 electron volt is equal to the same from this equation. Okay, EC plus EV by 2 plus 3 by 4 kBT ln of, what is MP star? MP star is nothing but MH star, which is 5. So MP star by ME star becomes 5 ME star by ME star. So what do you get? ME star gets cancelled. You are left with ln of 5. So now what do you need now? You need the temperature. So how can you get temperature? You have something which is LHS from 1, which is EV plus 0.6. If you just shuffle this, I just wrote it in a reverse way. So if this is all LHS, and if you subtract 2 from 1, the LHS will go off, remaining something which is the difference of 0.78 and 0.6. And on the RHS, you have EC plus EV by 2 and EC plus EV by 2, which when subtracted will disappear because it becomes 0. And then you are left with 3 by 4 kB, you know the value. So now if you want, what is it that you need now? You need T. So if you want T, subtract 2 from 1. Okay. So you will be left with simple calculation where you can end up with the answer of T as 1729 Kelvin. The only logic here is you will have to understand. So you will have to understand this shift of the level. Okay, the shift of the level has to be understood. The shift of the level first is EF is EV plus 0.6. Later is shifted to 15%. The shift of 15% is nothing but 0.18. So 0.18 shift by 15%, which has to be added with respect to EV, which is EV plus 0.18. 0.18 of what? The 0.6. The 0.6 gap. The 0.6 gap has shifted to 0.18. So you have to add 0.6 to 0.18, which will give you 0.78. So now your Fermi level is at EV, from EV, it is at 0.78 electron volts distance. So you have to add EV with 0.78 electron volt. Okay, so that's what the logic in this problem lies wherein. So please try to follow it carefully and substitute all the values, constant values which are given for you on the right hand side. So it will be very easy for you to end up at the answer. Coming to the third problem. For silicon semiconductor with band gap 1.12 electron volt, determine the position of the Fermi level at 300 Kelvin if Me star is equal to 0.12 m0. M0 is the rest mass of the electron and Mh star is again 0.28 times of the rest mass of the electron. So what is given? Eg is given 1.12 electron volt and T is given as 300 and Me and Mh star are also given in terms of your rest mass of the electron. And you know this formula already, which we have done previously. So now Eg is what? 1.12 electron volt. And so you can just substitute kb, you know all the values. So just substitute there. But in the second term, it's better you convert the kb, which is in joules, to electron volt. Okay, because you are given Eg in terms of electron volt as 1.12. So please convert kb which is 1.38 into 10 to the power of minus 23 joules into electron volt. That's all. If you are substituting again MP star as 0.28 m0 and ME star as 0.12 m0, the m0s gets cancelled and you are left over with some numerical value. Take the logarithm of it and just simplify it. So for those who cannot do it, I'm just substituting all the values. Okay, Eg is 1.12 electron volt by 2 because Eg is given as 1.12 electron volt and T is given as 300 Kelvin, and Me star is given as 0.12 times the rest mass of the electron, and Mh star is given as 0.28 times the m0. Okay, so now what is it that you should need to find out? EF is equal to how much? So now if you substitute all these values, 3 by 4 into, yes, so now 1.6 into 10 to the power of minus 19 joules, if it is equal to 1 electron volt, then how much is my kb, which is 1.380 into 10 to the power of minus 23 joules, equal to how many electron volt? So you get how much? 1.380 into 10 to the power of minus 23 by 1.6 into 10 to the power of minus 19, right? So just substitute that here. So 1.380 into 10 power minus 23 by 1.6 into 10 to the power of minus 19 into T is 300 Kelvin ln of. So ln of 0.12 m0 by 0.28 m0. So m0 and m0 gets cancelled. Just go for the simplification. That's all. You will end up in the answer, which is 0.576 electron volt. Okay, so going for the next formula, calculate the Hall voltage developed across the width of the slab of a metallic slab. It's width of a metallic slab. Yes, width of a metallic slab carrying a current of 30 amperes. So I is given as 30 amperes and magnetic field is given as 1.75 Tesla. And the magnetic field is perpendicular to the plane of the slab and to the current, which is the novel picture of the Hall effect setup. Okay, not setup, sorry, the principle. Okay, the Hall effect principle. If you see, if you have listened my class, you can easily understand how the magnetic field goes perpendicular to the current flow. Okay, so now the thickness of the slab is given here. Thickness is given as 0.35 centimeter and the concentration of the free electron is given. So N is given as 6.55 times 10 to the power of 28 per meter cube. So what you should find out? You should find out the Hall voltage. That's all. How much? So we know the formula for Hall voltage is this. And where RH is equal to 1 by NE, just substitute that because you are given N. So RH is not given for you directly, but it is given, RH is given for you in your hand because you know the value of E, and just substitute that given N and E. That's all. You will get a 1 by NE is 6.55, 10 to the power of 28 into 1.6 into 10 to the power of minus 19. You'll get RH. Substitute all the given values for you directly. Okay. B is given 1.75 Tesla. T is given 0.35 centimeter. But here there is one thing which you should do here. You have to convert this centimeter, convert into meter. Convert into meter. 100 centimeters equal to 1 meter, which is nothing but 10 to the power of 2. So 0.35 centimeter is equal to how much? How many meters is it? 0.35 into 1 by 100. So 10 to the power of minus 2 meters. Just substitute that here and you'll get everything. Okay, so what do you get? 1 by N is given. I have taken E. Okay. I, what is I? 30 ampere. And B, what is B here? 1.75 Tesla. And 1 by N is 6.55 into 10 to the power of 28 into 1.6 into 10 to the power of minus 19. Okay. So this RH, whatever you get, you go and substitute there. So VH is equal to some X. If you answer X into I is 30 into B is 1.75 by T is what? 0.35 into 10 to the power of minus 2. So this is what you need to do, and you will end up at 1.116 microvolt. Okay, so this is what you need to do. If you want, you can comment in the comment box with RH value separately, or else you can just substitute even directly as VH is equal to IB by NET. You can even write like this and just substitute everything, and you will get the final answer even. I have given this why? Because I want you to understand the relationship between RH and NE, because in the coming problems you can just correlate why I have told this to you. Okay, so now moving ahead, find the carrier concentration and mobility. If RH of a specimen is 3.66 into 10 power minus 4 meter cube per coulomb, its resistivity is 8.93 times 10 raised to the power of minus 3 ohm meter. So what is given, what you should find out? So RH, which is the Hall coefficient, is given as 3.66 into 10 to the power of minus 4 meter cube coulomb inverse. And resistivity is given as 8.93 into 10 to the power of minus 3 ohm meter. What you should find out? N you need to find out, and mobility you need to find out. And you know very well RH is equal to 1 by NE, right? And you have RH, you know E, so it's very easy for you to find out. 3.66 into 10 power minus 4, from this I'm going for, equal to 1 by N into 1.6 into 10 to the power of minus 19. So from this you can calculate N, right? You can calculate N. N is equal to 1 by 1.6 into 10 to the power of minus 19 into 3.66 into 10 to the power of minus 4. So you'll get N. Okay, so now mu is equal to RH by rho into N. How did I get this? Sigma is equal to NE mu, and so rho, which is equal to 1 by sigma, is equal to 1 by NE mu. 1 by NE is what? RH. RH by mu. So mu is equal to RH by rho. That's how you got this. Okay, very neat conversion. Nothing to feel confused. So now you have N, and you have to now find out, substitute that N here. You have rho, from this you substitute, RH from this you substitute here. So you will end up in N as 1.70 into 10 power 22 and mu as 0.041 meter square volt inverse and second inverse. Okay, so now going for the next problem, calculate the density and mobility of charge carriers of semiconductor given the Hall coefficient is minus 6.85 into 10 power minus 5 meter cube per coulomb. How can a Hall coefficient be minus? Can it be minus? Yes, it can. If the Hall coefficient is minus, what does the semiconductor be? It should be N-type semiconductor. RH is equal to minus 1 by Ne for N-type, and RH is equal to plus 1 by Ne for P-type. Okay, and electrical conductivity is also given. You need to find out density is nothing but again N, and mobility is mu. Okay, so now we know the same formula what we have used before, and we know this. So just substitute and you will get this answer. So nothing much to do here, the same problem. Okay, so please do it. And the following data are given for intrinsic germanium at 300K and Kelvin again. So Ni is 2.4 into 10 to the power of 19 per meter cube, and mobility of the electrons is given as 0.39, mobility of the holes is given as 0.19. You need to calculate the resistivity. This is the same formula, but here you are asked the intrinsic germanium, means it comprises of both the electrons and holes as the charge carriers. So you are given both the mobilities of the electrons and holes, and just substitute all those, and then you can get the answer. Okay, so how can you do that? So from this, Ni is given as 2.4 into 10 to the power of 19 into 1.6 into 10 to the power of minus 19 as charge of the electron into 0.39 plus 0.19. So then you should end up with this, and take the reciprocal of it by whatever you get here. You'll end up in this. So that's E if you don't know. Thank you for listening my lecture, and in my next lecture we will be starting module 3, and please collect some more problems from your textbooks if you find out, so that you can practice very well. And I hope you have followed along with me all the calculations with the concept. You should learn the concept, you should understand the concept, where you are applying and why you are applying. So meet you again in my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.